Fine. So yesterday we learned how to transfer your design into the schematic capture of ALTIUM designer. Now today we are going to see how to convert this schematic into a PCB artwork. So yesterday when we left off, we said that all the footprints which were necessary for the PCB were already available except for this nano. So nano we have not attached, or say we have not connected any footprint to that. Okay, that is where we are supposed to start our work today itself. So how do you make a footprint? A very simple thing would be to search for the mechanical dimensions of such a kind of device. Now here in this case it is Arduino Nano version 3. So I have already found out the mechanical dimensions, and you can see now. Do you see the mechanical dimensions in front of you? Are the dimensions visible to all of you? This mechanical drawing?
Yes, that's visible.
Okay, so if you closely see that it is all given in millimeters. Okay, and this is exactly what we are supposed to use for making the footprint. So you start with file, new, library, and then you can have a PCB library. Okay, immediately the screen will now change to a different window. It is starting, just hold on for some time. Okay, now do you see that the screen has now changed, the window has now changed in appearance, and we now have a new component over here. We'll just rename that component to Nano V3 whatever. Okay, right. At the same time, make sure that, as you can see on the lower left hand corner, all the dimensions are in mils, which is an imperial standard. Let us change that to, one second, let us change that to the metric standards. So here in PCB, you have the facility to change to metric dimensions. Let me just find out where it is, because I've been using a different version altogether. So project options, you don't have that. Tools. ALTIUM designer has recently changed their okay, there is another way in which you can do that. Instead of so edit, you can toggle the units from mils to millimeters. So what I did, view, toggle units. Okay, so I went into the imperial, from imperial system to the metric system, because that is easier for us to understand rather than. Okay, so what you see over here is the origin. Basically this is the origin. You can change the grid size also. So again, let me see where I can change this. Here we don't have that. Should be in preference itself somewhere. So anyways, let us not go into that. Now you can see here that my grid has now changed, and here is the starting point. for my footprint design. Now, if you refer back to this, so basically what we are going to do is we are going to lay out the pads in this particular order itself and respecting all the dimensions. So the very first pad, now this indicator over here, the origin is where we will be having the very first pad. So you can say place a pad, and there you can have placing of the pad here like this. So this is the very first pad that I am placing, and with respect to this pad, all the other entities we are going to place. If you look at this very carefully, you'll see that the distance between the parallel rows of the pads is 15.24. Okay, whereas the distance between two pads is 2.54, which is the standard pitch. This is called as a pitch, distance between the pins of the component. So we are going to use 2.54 as the measurement step. So again, I'll place pad, the second one, and just make sure that it is, let us say, if I start here, it will be 2.54. Now you can see here on the left hand side corner, lower bottom corner, that this particular pad position is exactly at 2.54 millimeters down from, that is the y dimension is down from the first pad. So we are on the right track. Okay. Similarly, I'm going to place all these pads on these grids. So just you can just count this 1, 2, 3, and 4. So place. So again, so here. Now this placement is very crucial because this is actually going to decide, going to determine whether your component really fits properly or not. Otherwise, there will be a problem. If you don't follow this properly, it's going to be a big problem. Your component simply won't fit inside the PCB. So let me just finish this off. We require 15 pads corresponding to the 15 pins on the left hand in one row, and similarly on the other row. So that is it. So this is our first row. Now you can simply copy and paste this, but I will not recommend that because we are supposed to find out the distance between these parallel rows of the pads. So corresponding to this, it will be 15.24 millimeters to the right of this first pad. Okay, so I will say at the same time make sure that the numbers of the pins are proper. So from here I can travel all the way and find out 15 point. There it is. So I can just simply make sure that this is not the 16th pin, this is the 30th pin. So I can directly double click this and change the designator to pin number 30. Now I have to work backwards. From here again, I can say place pad. So maybe I can start from here also. No problem with that. So go all the way. Now using the cursor, you can go for fine adjustments. Okay. Just make sure that you have correctly selected the distance. Now the interesting thing is that even if a footprint is not available, you can create your own footprint. That is the beauty of this software. So there it is. So I think we have messed up with the pin number somewhere. So we should start with 16, 17, 18, and so on. This pad seems to be a little bit off track, I guess. So you can see, yeah, it really is off track. So maybe, yeah, this is it. 2022. 24, 25, 26, 27. Still there is a problem, I guess. 17, 23, 24, 25, 26, 27, 28, 28, 29, and 30. Now we have the outline of we have the pad positioning of the component. Let us save this. So we'll rename this as my footprint. Okay. That is the name of the library. Now, if you want, you can still go ahead, and you can see that we have to trace the outline. So this is the outline of the board, of the development board. So what we can do is uh, you can simply there are 4 holes over here for mounting purposes. So you can either um, place the holes over here like this, and then you can estimate what will be the boundary of this device. Okay, so let us do that. So the hole is at a distance of 2.64 millimeter. The hole basically from the first pad itself. So what we can do is again place a pad itself, but at a position of 2.64. It may not be exact. So what we have to do is we have to make sure that it is exact. Okay, so you can place it anywhere as a matter of fact, and then you can fine tune it to make it 2.64 from here. There it is. So this is a hole which has been created here. Am I audible? Hello?
Yes, sir.
Okay. So now we have a hole here, and from this hole again we are supposed to have another hole which is over here, which is at a distance of again 15.24. So again I can copy this and paste this somewhere here. Of course, I'll have to make sure that it is 2.64. So that is how these mounting holes are there. Okay. Similarly, we have mounting holes over here also, but now the distance is 2.54. So just simply paste it here and here. That's all. So we have the 4 mounting holes also. Now what we are supposed to do is create the boundary. Now this boundary is not very clearly mentioned as from the point of view of the dimensions. So you have to make sure that your boundary, whatever you are drawing, is slightly bigger than the device boundary itself. So what I will do is, you have to select the top overlay layer for that and place a line. So we can simply place a line from here, draw it all the way like this. Just don't forget to close the boundary properly. So there it is. So that is our component, footprint of the component. Just save it. All right. So we already have the reference with respect to pin number 1. So this is our new footprint. In fact, you can make a 3D model out of this at the same place. We don't have that much time to do it, so I just leave it to you. So okay, one more important thing is that we are supposed to increase the pad size. As I said earlier, that upon drilling, the pad size, this annular ring will decrease, and so it is quite possible that while soldering, this annular ring may come off the board. It may get unglued from this board, and it will be a very bad thing to happen. So what we can do is we can increase the pad size here itself. So what I'll do is I'll just select the components, select the pads, all the pads, or a simple way to do it will be to right click, find similar objects, all right, and then what we can do is we can select the matching attribute as the hole size, because we don't want to increase the hole size for the mounting holes. So once I do this, I'll click on OK. So it will be selecting all the 30 objects from this PCB lip inspector. What you can do is you can simply change the X size or the Y size. Now let us see what happens to this if I change the X size to, let us say, 2 millimeters. See what has happened? The pad size has now increased in the X direction. This is exactly what we want. So I've increased the pad size for all the pads over here. Just to make this pad a little bit different, I just change the shape to a rectangular pad. So this is distinguished that this is pad number or pin number 1. That's all. So once you save this and go back to your my symbols, here I can now add the footprint. From here it automatically gets added. So here you can simply add the footprint. Okay, now what we have done is we have created a new footprint and we have attached that footprint to the schematic symbol that we have created yesterday. Okay, so now we have to update from the libraries. Anyways, so here also you can add a footprint, doesn't matter. So we have multiple ways of doing that. Okay, so you can see that the footprint is now added to this. All right. Okay. Fine. So now this schematic is ready to be exported or converted into a PCB. Okay. For that, again, what you have to do is file new PCB. So we are going to start a new PCB document. So as you can see again, that the screen has changed to a different view. Again, I'm going to toggle this to the metric system instead of the imperial system. Now here I can have the board options. Here also you can see that you can change it from imperial to metric directly from this place. Grid size I will change to a different one. Let us say 0.1 mm and then click on apply. Okay. So now what I have here is a blank board. I have to decide the shape of the board. Now, in order to do that, click on View, Board Planning Mode, okay, and then you can click on Design, Edit Board Shape. Now, what I'll do is I'll reshape the board. First of all, make the corner as the origin itself. Okay, there it is. And then I can change the size of the board also. So currently it is somewhere like 140 mm across and 86 mm. Let us keep it that way. Later on we can see if we can so we can save this as again the main PCB main board of our system. So now we are in the board planning mode. Again, go back into the 2D layout. Okay, now once you do this, go back to your main the schematic, and from here click on design and update PCB document. Now this is these are called as the mappings or the macros. Okay, so we'll validate all the macros over here. You'll see that all the macros are validated. We don't want to add what is called as a room here. Just make sure that you don't add that. Even if you add that, we can remove it later on. and then you can click on execute changes. If everything goes fine, you'll get all the green check marks here. If it doesn't find the footprint, it will trigger off an error. So you can see that all my components are now available on this PCB board or the PCB document in the form of their footprints. For example, this is the LCD footprint. You have this as our nano. Then this is your BS1307. This is the crystal. Now, first of all, bring all these components onto the board. Then we will place them properly. All right. Okay. Fine. So now once we have this, you can place the components. Now placing the components is a very tricky thing, because ultimately the routing effort that is required will be based on these things. So for example, if I do it like this, this is our sensor. So let us keep our sensor separate somewhere here. Of course, I am using a huge board size, which is really not required. We can cut down the board size once we are confident that my routing will be okay. So just make sure that the components are placed in such a way that the routing becomes easier. Now that is going to happen with experience. Okay. So let us now see whether we can route this these components or not. So for that, I'll just save it once again. Go into the design, the design, and into the rules. Now here you see a plethora of all the design rules. Don't get intimidated by these things. What is important for us is this routing. Okay. In that we have some certain rules. So the width. What should be the width of the track? Now, as I said, we have most of the times what we do is for power lines where you have VCC and the ground, we use 1 millimeters unless and until you require more current flow. And for signal, we require or we use 0.5 millimeters as the track width. So here what I will do is now I want to have a selective kind of track width setting. So what we can do is I can first of all name it as power, then go for custom query builder, and if the track belongs to ground, add another condition, belongs to, make sure that it changes to or changes to VCC. Okay, so this is the condition that we have set, and for these selective conditions the track width should be 1 mm. This is our first rule. You can say apply the rule, that's all. So what the compiler will do, what the auto router will do, it will automatically select, depending on whether it is a ground wire, a ground track or a VCC track, it will make sure that the track width is 1 millimeters. Okay, not otherwise. Then we have to set another rule. We call this rule as signal. And of course, all the tracks should follow this rule except for VCC and ground. So I'll just make this 0.5, 0.5, 0.5. Okay, and apply. Now the problem is, if you don't set the priority, all the code will be routed using 0.5 mm tracks. So I have to set the priority here. So I'll say power increase priority to 1. Okay, that's it. Say apply. Now let us see one more constraint or rule, which is again the clearance constraint. So you can see here that I can set the minimum distance or allowable distance between a track and a pad, or a pad and a pad, and so on and so forth. So we'll keep the distance between the track as 1 mm, between two tracks as 1 mm. We don't have SMD pads, but we have through hole pad. So through hole pad 1 mm. So this is what is our clearance rule. Again, you can apply. Now you are actually ready for the PCB auto routing. So click into the route, and click on auto route and say route all. And you can see that your board is already completely auto routed. It has not flagged off any error, or let us say it has not flagged off any failure to connect the net. So your first PCB directly is ready within seconds, like this. But we may require to change the size, because a lot of board size has been let us say wasted like this. So we don't want to do that. So I'll just unroot this and try to change this somehow so that I can compress the board to a smaller size. Let me see if this works properly. Again, as I said, placing is dependent on most of your experience, and you may find it a little bit tough in the beginning, but then you'll soon find it very, very easy to design your PCB. So what I can do is, again, I can go into the board planning mode, design, edit board shape, and simply reduce this board shape like this. Board dimensions, go back again here to this, and again go for auto routing all. Now it may not be simple, but yeah, I mean, it has completed already. So see, your first board is already there, it's ready, but it is a little bit raw in form. So what you have to do is, you have to just make sure that while manufacturing there won't be any problem. So you can manually edit these tracks also. For example, you see that this particular track, so we are actually using a double-sided board. So this red one is the top layer and blue is the bottom layer. Okay. Now you can see here it is very, very close to these pins. So I can just manually change these things here like this. At the same time, it doesn't have to go through here. It can go from here. So what I can do is I can break this track like this. Okay, fine. Again, you can just select the bottom layer and play around with these things. And make it a little bit more easier for the manufacturing process. You can simply edit it like this, no problem with that. Okay. And here also you can just expand this so that it will not be very close to the other pins. Okay, let us have a look here. All right, so I may have to break this again into angles. All right. This also can be simplified. This also can be simplified. Okay, I can have this from here. Okay, I'll show you if I'm not happy with this auto routing, what I can do is I can unroute a particular connection, for example this one, and then I can um, go for interactive routing, and then I can have the routing as per my requirement. Okay. All right. So you can see here that now we are finished with the board design completely. Okay. Fine. Now, if I want to see how it will look like after fabrication, what you can do is simply go into the 3D layout mode, and you can see here how your board will appear. Now, if we don't have the 3D models of the components, otherwise you can even see the board, which is how it will look like when it is mounted with the components. All right. So this is very easy to create. The software is very easy to learn. What you require is only a little bit of practice. Okay, am I audible still?
Yes, sir.
Okay, so I think this is okay. There is one more thing which is left, which I can tell you that many times we require to have what is called as a polygon core. May not be very good idea to use the polygon core here, but I'll just show you how to do it. So you can say click on place, and you go for polygon core, and then connect it to ground most of the times. Remove the dead copper. You can start just making so the general idea is that we are covering this all. Maybe this side will be more good for us. I'll just show you a small section. So we don't want any you can see that it is now having this kind of appearance. This is called as a polygon core, and most of the times wherever you require to increase the ground plane so as to absorb the noise, we can make use of such polygon cores. Now this can be connected to the bottom layer, or it can also be connected to the top layer. This is just the idea, which I mean the concept of polygon core, which I wanted to show here. So as you can see here, it is connected to the net. Wherever there is ground, it will be connected there. For example, here it is connected. See, it is connected to the ground. All right. All right. So This is how it will look like on the bottom side. Bottom layer, it will look like this. Now you can change the pattern also. It won't change directly, so you'll have to go for pouring the polygon again. Hatched. Start like this. So you may have something like this. See that? So this is how you can increase the ground plane and correspondingly make it more immune to noise. Specifically, when you have analog signals, these kinds of polygon cores are very, very important. Specifically in the when you are designing a power supply, a PCB for a power supply. So this is it. All right. So yes, I've finished with whatever was the objective for you to walk you through the process of PCB artwork design.